Any question? Okay. We have a question, a curiosity. You say that chemometrics can offer a set of tools, of methods that, in this case, you focused on cultural heritage and neutron spectroscopy, but which other kind of spectroscopy could take advantage of these techniques? For example, if your other example that can be interesting for the other.
Sure. The cases are wider because, for example, the last month I helped a colleague to understand how his MCMP code didn't work. So I used the PCA, and we discovered that there are some parameters because the user then gets into a particular detector. So we have discovered that the cover needs to change in some parameter. So we are focused in a particular length of the beam line. You can imagine that a beam line, for example, Vespa, is long 60 meters. So when we do the calculation in order to develop a new beam line, we have to know exactly the Newton transport and the different detector. And so it's important because it's a consuming time, so we have to know exactly what kind of data we have to manipulate. This is a case, but I show you before that from medical, from biologic, for a very large kind of field, the PCAs works very well. So if you have data, big data, you can contact me and we can do a very good work, a very good team.
Okay, thank you. Other questions? No? Okay, thank you. Again. Okay, we have a small variation with respect to the schedule. We go with Paolo Mocci, okay, and optical and electronic properties of BNN ring insertion in circumnessence. The case of Correlene and Novolene. Thank you.
Good morning. I present a discussion on the electronic and optical properties of Born-Nitride ring insertion in circummachines, analyzing the case of cornene and ovalene. Polycyclic aromatic hydrocarbons are small molecules that are usually employed as active elements in many optoelectronic devices. They offer several advantages like the easy purification, evaporation, and solution processing, and they show tunable electronic and optical properties. Among them, the circummachines have recently attracted our attention. In fact, this small-sized molecule can be considered as finite portion with a nanometric dimension of the graphene, the infinite system, the infinite counterpart. So, some details about boron nitride. Boron nitride compound is formed by the union of boron and nitrogen in the same amount, and it shows up as a heat and chemically resistant refractory compound, which present very crystalline forms that are isoelectronic with respect to the elementary form of carbon. We can see, for example, some carbon-made analogues, like the hexagonal form, which is the counterpart of graphite. This is the most stable and soft form among the BM forms. The second form is the cubic one, which is the counterpart of diamond. Its extreme hardness, wide energy band gap, low dielectric constant, and the high thermal conductivity are very near to those own of diamond. And finally, there is also a potential use of Bohr-nitride system in nanotechnology devices. For example, the Bohr-nitride nanotubes are the counterpart of the successful carbon-made nanotube. The recent success and surge in graphene and carbon-based research material has stimulated also the interest of other 2D nanomaterials, like, for example, in our case, on the 2D Bohr-nitride. In fact, 2D Bohr-nitride-based nanostructures are considered as ideal candidates for different technological devices and applications, going, for example, to vacuum technology, microelectronic devices, wear resistance lubricant, GPUV LED, devices for graphene engineer, and also for biological and medical applications. Some advanced applications, for example, in optoelectronics, the doping with atoms of europium can turn a Bohr-nitride nanotube into a phosphor material which emits visible light. Or compared with conventional hard materials, these hybrid forms carbon and Bohr-nitride compounds, in addition to being harder at room temperatures, maintain these hardness over a wide range of temperature. And finally, for what concerns health issues, after the test of biocompatibility through toxicological investigations on Bohr-nitride nanotubes, the test of the high chemical inertia favors the potential use of Bohr-nitride nanotubes in biomedical field as gene and drug transporter. However, there are also some differences between the two compounds that are mainly due to the different nature of the chemical bond involved. In fact, for example, if HBN is an insulator, on the other hand, the graphite is a conductive semimetal. Or if the cubic BN can be doped either N and P-type, diamond can be doped only as a P-type material. So, in this work, we present computational analysis on the optical, electronic, and transport properties of some Bohr-nitride rings, substituted molecules, which could be of interest and very attractive for the potential used in condensed matter physics. We have selected the case of chlorine and ovalin, that are the two first molecules of silcomacines, analyzing their pure carbon-based form and their Bohr-nitride ring substituted shapes. We have performed density functional theory and time-dependent density functional theory calculations using a localized Gaussian basis set combined with a hybrid exchange correlation functional, the B3 life. This permits the calculation of the electronic properties and to obtain the optical absorption spectra and some transport coefficients. So we discussed the possible implications of these general trends on the physical observable, comparing the carbon-based compound with respect to these hybrid carbon Bohr-nitride clusters. As computational methods, first we have used the DFT, implementing in the Gaussian system code to compute the ground state properties. The Gaussian basis set is the 631 plus G star, and the hybrid functional is the V3 life that includes a portion of the excited change from the Hartree-Fock theory, and is a combination of back exchange Li-Ampere correlation functional as the following expression shows. As a second method, we have implemented the TDFT calculations to compute the optical properties and to obtain the absorption spectra. In particular, the spectra are obtained from the calculation of the pole of the poles of the polarizability function in the frequency domain through Casida scheme. These poles represent the vertical excitation energies, while their intensity corresponds to the oscillatory strengths. And finally, we have used the delta self-consistency method, through which we can calculate the vertical electron affinities and the vertical ionization energies as total DFT differences, considering both the neutral and the charging species. And finally, we can also compute the quasi-particle gap, also known as the fundamental gap, which is defined as the difference between the vertical ionization energy and the vertical electron affinities. Finally, we can also evaluate the exciton binding energy with an approximated method combining the delta self-consistency method and the time-dependent DFT, as the differences between a gap and the opt, where a opt is the optical onset visible in the absorption spectrum. So here are the molecules under study. We have the coronin and the ovanin that are the parent of the original molecules in the carbon-made forms, and then the substituted one. Coronin with ring substitution and ovanin with ring substitution because it is made in the inner core. And last, the stripe substitution will concern 3 or more rings in the case of ovanin. So here, while table 1 presents all the computed data derived from DFT calculations, the same computed data are reported through a live depiction in which we can see that passing from coronin to the stripe substitution with boron nitride, we can see that there is a general decrease of the vertical ionization energy, a general increase of the vertical electron affinities, and a consequent reduction of the quasi-particle gap, the black arrows. This situation is similar in the case of ovanin, in which we can see also, in this case, a general decrease of the vertical ionization energies, a general increase, but a slight, in this case, with respect to coronin, and a reduction in the case of the fundamental gap. For what concerns the optical properties, we have analyzed what happens for what concerns the fundamental gaps, optical onset, and exciton binding energies. In this case, all the computed data derived from TD-DFT calculations are reported in the table on the left, while the results are presented through a live depiction in which we can observe that there is a reduction for both, in this case, the fundamental gaps and the optical onset, passing from the carbon-made molecule to the boron nitride substituted one with a trend, a visible trend, and also in this case of the exciton binding energy. The situation is quite different for what concerns the ovanin family, because in the case of the exciton binding energy of ring substitution, the exciton binding energy has a reduction when compared to the other members of the family with a not monotonous trend. Then we have also calculated and reproduced the absorption spectra, comparing the carbon-based parents on the left coronin and on the right ovanin in their substituted shape. We can observe that the main absorption peak, typical of the pure carbon-made parents, is redshifted in the case of ring substitution for both coronin and ovanin, while the situation is reversed as the amount of boron and nitrogen atoms inserted into the original matrix increases because there is a reshift of the main absorption structure and a redistribution of the intensity at higher energies. Finally, the last theme analyzed is about charge transport. Inside organic-based material, charge transport can be studied as a combination of two main processes: the intermolecular carrier movement and the intermolecular charge transfer. And transport may occur through a hopping process. There are structural similarities between graphene and HBN that, combined with their dissimilar electronic properties, allow for the formation of stable hybrid systems and permits the creation of a new system with novel electronic properties and that are very easy to enable. We have computed the molecular organization energy, lambda, which is the sum of two contributions, the inner and the external terms, but we only computed the last term because the first one can be neglected. And the method used is the 4-point method, according to which lambda can be defined as the sum of the radical anion formation energy and the relaxation energy of the charged species, as the following expression shows. So, transport properties is described in semi-classical Marcus theory, but we only limit our analysis on the calculation of lambda, and we not compute all the set of transport coefficients because it's next future work. So we can see our computed data in the table for both the hole and the electrons, and we can analyze in these plots that for both coronine and ovalin, lambda for electron and holes rise as the amount of boron and nitrogen atoms inserted into the carbon-based matrix increases, but there is a sharp reduction of mobility because lambda increases in the case of boron nitride stripe type substituted molecules. So the conclusion for what concerns transport is that charge transport seems to be favored in carbon-made for ovalin, since lambda is little, while in the case of boron nitride ring substituted coronine instead of the carbon-based compound. Conclusions follows because we have analyzed what happens in the passage of carbon-based molecules and boron nitride ring inserted ones. For what concerns the electronic properties, we have found that a general increase of the vertical electron affinities, a general decrease of the vertical ionization energies, and also of the quasi-particle gaps take place. For what concerns the optical properties, we have found a redshift of the main absorption structures in the case of ring substituted forms, while a blue shift of the main absorption structures in the case of the stripe type substitution, and a redistribution of the amplitude and energy in the UV and not more indivisible. And finally, for what concerns transport properties, it seems that at this level of evaluation, without the computation of all the set of coefficients concerning transport, but limiting our analysis on the lambda, on the molecular organization energy, we can see that our hypothesis is that carbon-made regional parents or system with a small amount of boron and nitrogen inserted into the matrix favor transport. So, thank you for your attention.
Any questions? Okay. I have a curiosity since I'm working with carbon nanotubes, and I know from the literature there are many applications for many biological applications in which one wants to take advantage of the optical also absorption and emission. But one of the main problems is that carbon nanotubes are have some concern from the toxicity point of view. I think that is very interesting, the fact that probably using boron nitride variation of the carbon compounds, one can reduce the toxicity, and if you have some answer from this point of view, and what is the range of tunability depending on the variation of the structure with boron and nitrogen?
Okay. Yes, in fact, a very good question and curiosity, because boron nitride nanotubes favored the use as gene and drug transported because they are not toxic, and also they are inert. And so this potential use could be developed in medical field. And also for what concern the boron nitride compound is very resistant from a thermal and chemical point of view as compared to carbon. With respect to carbon, is favored for this reason in principle, and also to modulate the optical and the electronic properties. For example, we have seen that these molecules, these carbon molecules, absorb indivisible, or also in the IR, for some molecules absorbing the IR, while modulating, increasing the amount of boron and nitrogen atoms in this hybrid carbon boron nitride system, we can blue shift the absorption at high energy, so in the UV. And so the system can be very useful for deep UV lab, for example. But the range of application is now is going to be developed also in the next future, and also for what concerns transport, child transport, maybe.
Okay, thank you. It's very interesting, the tunability.
Yes, the tunability is very easily tunable.
Okay, thank you a lot. Any questions? No? Okay, so thanks again. Okay, now I'll introduce you Zagaglia, analysis in reciprocal phase of the bandpass filter effect in uniform and non-uniform grading counters. Okay.
Okay, good morning everyone. First of all, I'd like to thank the committee for having me here at the 10th Young Research Meeting here in Rome. I'm going to talk about the analysis in reciprocal space of the bandpass filter in the uniform and the uniform grading coupler. But first of all, my name is Luca Zagaglia. I'm a PhD student at the Tyndall National Research Institute in Cork, Ireland. And as you can see, Ireland is not just fairies, leprechauns, and pot of goals, but sometimes, as you can see from the image of the research center, there is also sunny weather sometimes. And I'm working in the photonics packaging group. So the idea is to try to couple the light from whatever is your external world inside a photonic interface circuit. So to choose what you call peak. So first of all, I'm going to talk about the general problem that we have in coupling the light inside a peak. The general type of solution that we can use that is a grading coupler to overcome this problem. And the structure that I'm going to show you are defined on a silicon insulator wafer that is called SOI. And then I'm going to talk about the bandwidth of this structure. So how we can see a difference and why we see a difference in uniform and uniform grading coupler in terms of the wavelength that we can couple inside a peak. And the analysis we'll do in using the Fourier transform and the best structure of the system. So first of all, the general problem that we have in coupling the light inside a peak is that there is a general mismatch in the modes. For example, in this case, in telecom application, we are using single mode fibers. As you can see, single mode fiber core is 8.2 microns, and the mode that is sustained by the fiber has a dimension in terms of its intensity profile of 10.4 microns at 1550 nanometer. That is a typical wavelength that we are using in the C-band in telecom application. And so if we want to couple this mode inside a peak, we need to put an interposed structure between the two, just because you see inside a peak there are features of hundreds of nanometers. So the general way that in which we study this type of problem is to use FDTD to resolve this type of structure, that is a finite different time domain computational method that allows you to resolve Maxwell equation in space and time and to get all the information that you need in terms of the propagation of the electromagnetic field. So as you can see here, generally there is the fiber on the top of the grating tilted at a certain angle, the angle that you want to use to tune this type of structure. With this cross section, you can see the diffraction process that couples the light towards the waveguide. The XY cross section is the top view of the grating, and you can see this tapered shape of this structure that focuses the light at the entrance of the waveguide. And the last cross section is the XY, where we collect the light in order to see if it is coupled inside the fundamental mode of the waveguide, and also to get the coupling efficiency of the system, so the amount of light that is coupled inside the waveguide. The major channel of losses of the gratings is the light that is back reflected from the grating and the one that passes through the structure and get lost inside the so-called substrate, so the green part here. So usually what we use is a uniform grating copper, so a structure that has a constant pitch, and non-uniform grating coupler or sharp grating coupler, where the pitch is changing linearly through the grating coupler. And if you resolve this with the FPTD method, then what you get is basically the coupling efficiency spectrum. So as you can see, a uniform grating coupler can reach roughly 60% of coupling efficiency, while if you use a nonlinear grating coupler, what you can do is to pump the coupling efficiency to the value of 85%. Those are, of course, from the simulation point of view. However, if we consider the uniform grating coupler, then the bandwidth, so the ranges of frequencies that we can couple, is 45 nanometers, while using a non-uniform grating coupler, it is reduced to 30 nanometers. So if we take the percentage difference, it's roughly 30%. So it's quite a lot. So how can we study this bandwidth reduction? So the first thing that we can do is to collect the emission of the grating coupler, because this type of structure can be used to upcouple also the light from the peak, and to look at the Fourier transform of the emission of the grating. And so we can get the spreading in the energies in terms of the K, so the wave vector. So as you can see, first of all, the uniform grating coupler has a uniform Fourier transform if we divided the plot into two parts. Instead, the non-uniform grating coupler, as you can see, has a thicker region here and a thinner part here. So in terms of the energy, it's acting like a filter. If we consider a cross-section at K vector equal 1, this means that we are considering the wavelength at 1550 and an impinging angle of 10 degrees. That is the most usual one to couple the light inside the grating. What we can see is that we are able to get from the cross-section, again, the reduction of the bandwidth. So we get the 45 nanometers for the uniform grating coupler and the 30 nanometers for the non-uniform grating coupler. Moreover, we can see that there is, along this cross-section, a difference between the parts of the Fourier transform for the uniform grating coupler. Here we have a sharp decay. Instead, on the left part, the decay is more gentle. And this is suggested by the filtering effect, again, of our structure. To have a general overview and a better overview on this problem, what we can do is to take also the Fourier transform of our source, in this case, the fiber, and to get the overlap region between the Fourier transform of the grating coupler and the Fourier transform of our source. As you can see, again, we can get a uniform image for the uniform grating coupler that is spreading in terms of the energy, while in the case of the non-uniform grating coupler, we have a blurry region here that is close to the thicker part that I've already shown you in the previous slide. And in terms of the energy, the spreading is smaller. So the idea right now is to how can we study this problem from a more structural point of view. What we can use is to study the band structure, and we can define the band structure for the uniform grating coupler just because this structure is basically what is so-called a photonic crystal, because we have a dielectric periodic function. Yes, we have a dielectric function that is periodic. Instead, in the non-uniform grating coupler, it's not so easy to define the same band structure concept. So first of all, what we can use is, again, the FDTD method. So we can recreate our structure inside the simulation software, and we define our simulation box that has a width of the pitch of the structure, and setting a periodic boundary condition, we can use dipole source to excite all the modes of our structure. And using the time monitor, what we can get is basically the time response in terms of the electromagnetic field. And then doing the Fourier transform, we know the modes that are sustained by our structure. So if we consider the uniform structure again, and we are taking the band structure in the region of 0.8 electron volts, that means our 1550 nanometers, that is the wavelength that we use to tune this structure, and we get the overlap between the band structure and the Fourier transform of our Gaussian source. So again, the fiber that we're using to shine on the top surface of this object, then we are able to get again the bandwidth of our grating coupler. Instead, if we are considering a non-uniform grating coupler, in this case, the only thing that we can do, is to consider each period of the grating, reconstruct the uniform grating coupler associated with the different period of the grating, and to get the bandwidth of this non-uniform grating coupler. So as you can see here, the blue line is the first period, the 5th, the 10th, and the 15th. And in this case, we don't have any more, of course, just one line. But what we can see is that we can divide this plot into 3 main regions. So the light is coupled from the fiber into the central part of the grating, so around the 10th tooth of the grating coupler. This means that our Gaussian source is shining with its center on the 10th tooth of our grating. And so the majority of the light is scattered by this scattering point. Then the light travels through the grating coupler across this direction, so across the regions where the trenches of the grating, so these empty spaces here, are reducing in terms of their width. And what we see is that if we consider again the overlap with the Fourier transform of our source, all these energies are filtered out by moving across these trenches that are reduced. Then, because the majority of our scattering process again is going inside the central part of the grating, we can set the minimum level of our bandwidth at the 10th tooth, and so again we are able to get the 30 nanometers of the bandwidth. And this last part here are the tails of the Gaussian source that are coupled by the first period of our structure that gives this asymmetry inside the coupling efficiency spectra. So my talk, just to sum up what I already said, is that we have right now a problem in coupling the light inside the photonic integrated circuit that is mostly due to a mismatch in the modes between whatever is your external world and the structure and the photonic integrated circuit. The way to overcome this problem can be using uniform and non-uniform grating couplers. However, if we are considering a non-uniform grating coupler, we have a reduction in terms of bandwidth that we can study using the Fourier transform or the band structure of our system. And in future, what we'd like to do is to realize all this structure in order to make measurements and to confirm the theoretical part of this work. And finally, I'd like to thank the Scientific Foundation Ireland for supporting this work. Thank you.
Do you have any question?
Okay, I have a question. For the linear variation of the pitch, you consider just one kind of linear variation or different kinds? And in the first case, what kind of behavior you expect with different?
Okay, so I don't know if you're familiar with this type of topics.
Not too much.
Okay, so in general, the problem is that when we are optimizing like breaking couplers for this type of application, the problem is that we are using every time iterative algorithm. So if you have a black box, okay, that is optimizing your structure, you set your parameters that you want to optimize, and then you get finally the spectrum, and the coupling efficiency, without knowing anything about what's happening. So an idea is to use, as you see in the band structure, in order to get a flavor, a more physical flavor of what's happening inside. And maybe in future we can also import this type of study inside the algorithm itself in order to push a maximum limit the coupling efficiency. But because, of course, the matching impedance that there is inside the non-uniform breaking coupler, just because you are matching at each step the effective index of the mode that is traveling inside the breaking structure, now the linear function is the easiest one to use. And as you can study also the variation of the band structure for each period, well, just a second, where is the... here. So if you look at how the band structure changes, let's give you an idea of what you can use as function to to change the different ranges of the breaking coupler, just because the variation is in this case linear. And so if you're using, for example, a nonlinear function, then of course this matching impedance here it's not small enough to couple the light efficiently. That could be a okay.
Thank you.
No worries.
Any other question? No? Okay, thank you again.
Yep.
Perché non sistemare.
Prova. Okay, let's go on with one of your Mazzarisi. Condensation of fluctuation and their dynamics in the Gaussian model.
Yeah, I want to thank the organizer for the event and mention my collaborators, my supervisor in Salerno, Federico Barberi and Andrea Gambassi. And well, the occurrence of fluctuations is in the art of many physical phenomena. We had an example yesterday during the talk of Federico Tosone about in a cosmological context, for example. Typically, in extended systems made of a large number of microconstituents, collective quantities, observables, evolve as to stay most of the time close to their average values. And large fluctuations are really rare. So typically in application they are neglected. But there are situations where they can lead to important consequences. For example, when they lead to an absorbing state, namely a state where the system's a configuration that the system cannot escape. Examples of these are extinction of species, failure of devices, or a bankruptcy of a company. This latter was indeed the first problem where rigorous results of the large deviation theory, which I'm going to introduce, was used for the first time. So, the large deviation principle for an observable, for a collective quantity, is to be really synthetic and exponential approximation for the probability distribution describing it. So let's take an example. consider the sum of n random variables, which are independent in this case and identically distributed according to an exponential distribution, but it's just an example. And the probability distribution of S, assuming a certain value, so a certain fluctuation, is given by the exact solution of this integral. And in this case, this integral can be approximated with this exponential function, which is called the rate, with this exponential, where this function is called the rate function, and here we have the size of the system. In this case, it has this form, and there are general theorems to state if the large derivation principle exists for a determined PDF, or if it's not, and methods to calculate the rate function. And this function has general properties. In general, it's non-concave. It has a minimum in the average value, and it equals 0 there. So it's, if you want, an intensive function, and the PDF instead, it depends on the size of the system, and as the size goes up, it gets peaked around the average value. If we take the thermodynamic limit, the fluctuation disappears, and the observable assume only the average value. And this is a generalization of the central limit theorem, and it recovers it. Indeed, if you expand the rate function around the average, and you stop to the second order, it equals 0 there. It is a minimum, so you're left with Gaussian fluctuations. So, and let me introduce the general setting. Consider a prior distribution describing a system of finite size with microstates phi, which are a collection of the degrees of freedom of the system, where I can be discrete or continuous, and a set of parameters j, which can be the time or temperature. This can be the phase space coordinate of a gas in a box, for example. And the probability distribution for an observable defined on this system, on these microstates, is given by this equation as before. And I'm interested in fluctuations, in the structure of the fluctuation for observables in both equilibrium and non-equilibrium regimes. And in particular, to the fact that associated to certain rate fluctuations, there are peculiar microstates of the system. So a few lines of math. I will use large derivation theory, and from the probability distribution, writing the delta function in an integral form, we arrive at this point, where lambda is an important function of the theory called scale-Kuhlmann generating function. And performing a saddle point approximation, we end up with this exponential form for the probability distribution, where this is the rate function as before, which is nothing but the Legendre transform of lambda, and where z star for each value of m, the fluctuation, is determined by the saddle point equation. So the specific model I will focus on is the Gaussian model, which can be thought as the Bayer or Gaussian level, for example, of a constraint theory, of a constraint of a lattice theory. And it describes the scalar field with this bilinear Miltonian function in the general dimension, and R is the mass here. And I'm interested in non-equilibrium dynamics, non-equilibrium behavior, so I need dynamics. I use conserved order parameter dynamics, described by this Langevin equation. Usually, this is used to describe systems like mixtures of water and oil, for example. It's conserved because you can now transform water molecule in oil molecule, so the percentage of the two mixtures is conserved. And this is a very simple problem, and the solution is well known. This is the solution of the k-modes of the field in the Fourier space. And this will constitute my degrees of freedom. So the collection at a certain time, if out of equilibrium, at a certain temperature in equilibrium of these variables, will constitute a microstate. Now I need an observable to study, and through large derivation theory, and I choose this one. The variance, a very simple quadratic observable of the system, is the sample variance of the field, and this is the rate function I get, which tells me how the fluctuations behave. I have two regions, one which I call normal, and one which I call strange. And in this part, in this point, the critical point, there are discontinuities in the derivatives, and it rectifies here. And I call this condensation of fluctuations because all the value, for all the value of the observable when it fluctuates in this region, the microstates of the system are particular. I call them condensed because I will not go in details here, but when solving the saddle point equation to find how is the rate function in that part, you encounter a pathology at the critical point, and you solve this pathology using arguments really similar to that of Bose-Einstein condensation. These are related to, and this is integral over the modes, and you isolate the zero mode, which play an important role here. So this tells us that in that part of the fluctuation, when the observable assume one of those values, the contribution to the observable from the zero mode is macroscopic with respect to the others. And so we have this form of the rate function, which here follows the equation as before. And here is a straight line. Indeed, S appears linearly. This is why we call it condensation of fluctuation. There are more interesting things if we go and look at the dynamics. I choose a quenched dynamics. I choose as an initial condition I put the system in contact with the thermostat at the initial temperature, and then I change abruptly the temperature of the thermostat, and I let the system thermalize. And this is the picture we get. Here we see that there are three regions. One region when fluctuation throughout all the dynamics never get condensed. Here we have a permanent region where the fluctuations are permanently condensed. And here the fluctuations become condensed during the dynamics. And to have more insights on why this can be interesting, I have to mention that at equilibrium, if I prepare the system at equilibrium at different temperature, and plot the rate function against S over the average value, which is related to the temperature. I'm not showing you this, but trust me. And all these rate function at different temperature collapse on a master curve if I plot them against S over the average value. So in this case, this is what happened. This part, this brown part, is where fluctuation never condensed. And so they behave like adiabatically relax to their final state. So it's an equilibrium-like behavior. While the behavior for the condensed part is really more involved, more complicated. And we have an algebraic relaxation to equilibrium. So it's like the system has to organize in a more involved way. The structure of fluctuations when there is condensation have to undergo a more involved path to reach stationary state or equilibrium state. Yes. And a final remark is that if we consider this again, the probability distribution for the observable we're looking at, we can think of the rate function as playing two different roles. One, as I told you up to now, is that regulates gives us the information about the structure of the fluctuations for that observable. Another way we can look at it is that the thermodynamic potential for another ensemble, not the prior, which have been biased. And indeed, this one, in this case, can be thought as the partition function for this new ensemble. And this all will be the new probability distribution. So in this sense, the rate function for the dual is like a free energy. So there is this duality, and one can exploit tools from equilibrium statistical mechanics to study things. Indeed, we choose that observable in this case, because the dual model to this, in this case, is a well-known model. It's the spherical model of Berlin-Katz describing the magnet. And this model undergoes a phase transition from paramagnetic to ferromagnetic. And this transition is strictly related to the condensation transition we saw in the fluctuation of the other model. And also in the dynamics. Indeed, when the magnet gets quenched down from a temperature greater than Tc and goes low, it goes coarse graining, and indeed the size of the fluctuations grows algebraically. And we recover some, the same, something that resembles the more involved behavior that fluctuation with condensation has during the non-equilibrium dynamics. This can be interesting, this duality thing, because ideally, if one is interested in a specific phenomenon, could, in principle, follow two different experimental or numerical simulational protocols, either leaving the system unbiased and monitoring rare fluctuations, which can be, for example, really expensive or ineffective for simulations, for example, or can choose to constrain the system with an appropriate bias and studying the average properties. This also can be involved, sometimes because maybe the constrained system is really more intricate, so one can choose one way or the other. And okay, and that's it. And I complete my talk. Thanks.
Are there any questions?
Hello, thanks for your presentation. I've just got one question, like when you were talking about the thermal characteristics, like previous, not on this slide. Like it's not my field, and maybe my question is a little stupid. Yes, about this one. Like when I look at the graph, like from CP and like PC, like there are also all of them are the linear functions, right? So like, what's the difference? Like, what made the difference? I didn't get.
Yeah.
You can tell me.
You mean that
like why you separated like the middle part from the last? Like.
Okay, the last part is a straight line since the beginning of time up to the end. It's always a straight line. During all the dynamics, from the beginning to the end, the fluctuations corresponding to that region are supported by a condensed microstate. While in the second region, the middle region, at the end, at the beginning, fluctuation associated to those fluctuations in those regions are not supported by a condensed microstate, and condensation has to happen, has to render those fluctuations possible during the dynamics. And so, indeed, you see that while the critical point is shifting, actually, you see that the zero mode, the contribution of the zero mode, which I told you about, is microscopically contributes to the fluctuation when there is no condensation, and when the critical point passes through that value of the fluctuation, that corresponds to an explosion of the zero mode, which becomes macroscopically important at that point. So those are different because dynamically one is condensed from the beginning, the other has to pass all these stages. So
yeah, no, I understand. Thank you.
I have a curiosity, since you say you can put an appropriate bias to study something in the dual ensemble. And so it's possible to think, for each system, it's possible to think to different appropriate bias to study and come back to the dual system and try to understand what happened to the...
Yeah, theoretically it's possible, but it's really hard to think. I mean, in this case, this observable was interesting because that's this dual model which is well known. But for example, in another case where we studied also energy as an observable, and which has really similar properties. But in that case, there is no known model which is known about that. So in principle, you can think and start to look at possible observables in one case for the unbiased system, and think if that translates to some meaningful model. For example, another thing we are doing is thinking, I mean, this means that choosing that observable, it's like we are constraining the system, the dual one, with that constraint.
Okay.
The square of the field has to equals S for that particular fluctuation. So it's like constraining the system in that way. So, for example, we are doing something like thinking about an observable which will that is like choosing a spherical constraint. We were thinking about how to, for example, choose an external field applied to the dual. What observable in the prior correspond to an external field applied to the dual.
Okay.
Now this is the Gaussian model, so it's not really descriptive of even the easy model because you need the lambda phi to the 4. But this is it is didactic because even this simple model, which should not support condensation or averaging, is well known, shows this really rich behavior in the fluctuation. So we are on this model.
Okay, thank you a lot.
Okay,
Thanks again. So we conclude this session with Armando Galluzzi and silver doping effect of irreversibility field and pinning energy or iron-based superconductor.
Okay. Good morning to everyone. I'm Armando Galluzzi, and it's a pleasure for me to be here. And I would like to thank the organizers for giving me this opportunity to present part of my work that has been carried out at the Department of Physics in Salerno and CNR spin in Salerno, in particular in the Laboratory for Analysis of Materials Behavior in DC and AC fields. Thank you also to my professor, Massimiliano Borghetti. This is the outline of my talk. Initially, we will speak briefly on superconductivity in order to understand the framework in which we are moving. After that, we will introduce also iron-based superconductors, that is the kind of materials that I have studied in, and I want to present you in this work. The measurement system with which we have performed the measurements, the scientific results, and finally the conclusions. Okay, let's start with the superconductivity. A material becomes a superconductor when it is cooled below a particular temperature, called critical temperature. In particular, a superconductor is characterized by two main properties. The first one is the zero electrical resistance below this critical temperature. The second property is the so-called Meissner effect, that is the expulsion of the magnetic field from inside the superconductor, from inside the material. Now, we can have two types of superconductors.
the first type superconductor and the second type superconductor. As you can see, the first type superconductor is characterized by only one critical field, and the critical field is that field above which the material becomes normal. The second type superconductor has usually a lower critical field and an upper critical field. If we are below the lower critical field, we are in the Meissner state. If we are above the upper critical field, you are in the normal state. But what happens if we put between these two particular fields? If we put our field between the lower and upper critical field, we are in the so-called mixed state. That is a very important state in the superconductors, because it is characterized by the entrance of the magnetic field in the material in forms of quantized flux. So you have still superconductivity, but with magnetic field that is penetrated in your material. And this is a very important characteristic. In general, in the two types of superconductors, the second types of superconductor, there are, we can say, in an ideal case and a real case. The ideal case is characterized by the disposition of the vortices, the arrangement of these vortices in a so-called abricos of lattice, that is a very regular vortex lattice. But as you know, usually we are never in the ideal case, so we have also, and especially this real case, that is characterized by the presence of impurities that pin the vortices that has penetrated in your material. This presence of impurities facilitates the positioning of the fluxons inside your material, and the impurities act on the fluxons like a potential barrier. This kind of phenomenon is very important in superconductivity, and it is called pinning phenomenon. Now, after this introduction on superconductivity, we can pass to the iron-based superconductors. In particular, in 2008, the Professor Osamu in Japan discovered superconductivity in iron-based compounds. Why is this important? This is very important because up to 2008, up to this discovery, it was believed that the magnetism and superconductivity were antagonists. So it is strange to see superconductivity in compounds that have iron in their stoichiometry. But after this discovery, everything changed, and in particular in this kind of materials, iron-based superconductors, there are four families, and we want to study, and we are going to talk on phase A, in particular two samples, one undoped, that is iron selenium 0.94, and a second one that is an iron selenium 0.4 with addition of 6% in weight of silver. And in particular, I want to thank the Professor Nazarova and Professor Buchkov of the Institute of Solid-State Physics, Bulgarian Academy of Science, for providing these two samples. Now, let's see the measurement system that we have in Lambda laboratory, and in particular, our system that we have used for performing the measurements is a quantum design PPMS with option level pool. In particular, PPMS is an acronym that stands for Physical Property Measurement System, that is dotted of several inserts, VSM, ACMS, etc., with which we can perform several types of measurements, magnetization, transport, capacity, and other kind of measurements. In this work, we will talk about on magnetization measurements. Another very important characteristic of this PPMS is this option level cool true. Why is this important? This is very important because we can recondense and liquefy helium gas, and so you have no need to refill with liquid helium and liquid nitrogen your system, and this means that you can use continuously your PPMS. This is very important because, as you know, the liquid helium is very expensive. So in order to achieve hundreds of liters of liquid helium is very difficult for our fundings. So this option is very important. And this is, we will study in particular measurements performed with the vibrating sample magnetometer, so in DC magnetic field. This is a picture of the PPMS used at the Lambda laboratory in Salerno. Now, let's see the scientific results. And in particular, we want to study the effect of the silver doping on our iron selenium sample, right? We can start with this magnetization as a function of temperature measurement. And this was performed at fixed magnetic field of 30 Hz. In particular, you can see in this picture the black data are for the iron selenium, and the red one are for the iron selenium with doping of silver. From these measurements, the first characteristic that you can observe is the determination of the critical temperature. In particular, you can see that for the undoped sample, it is around 8.5 Kelvin, because it is taken as the onset of the zero field cooling curve, that is this one for the black, and this one for the red, that is the silver doped sample. And for the silver doped sample, it is approximately of near 9 Kelvin. And so you have an improvement of this critical temperature of about half a Kelvin. The second type of characteristic that we have observed is this critical current density as a function of magnetic field at different temperature. Now, what is the critical current density? The critical current density is a very important property and characteristic of the superconductors because it is the maximum current density that you can put in your sample without having dissipation. So also for the application of superconducting magnets, superconducting wires, this is very important because you want to avoid dissipation inside your material. Now, on the left panel, you can see the iron selenium, and on the right one, the silver doped sample. In particular, we can see that observing the scale of the critical current density, you have that the silver doped sample is has a critical current density much higher as the undoped sample, and in particular, especially at low magnetic field, performing between 0 Tesla and 9 Tesla, you have also that the signal for the silver doped sample is less noisy with respect to the undoped sample. And this indicates a stronger superconducting phase and a lower magnetic background in the sample. In particular, from this critical current density, you can extract also the so-called irreversibility field, using the criterion of taking the Jc equal to 100 ampere per centimeter square. Now, what is the irreversibility field? It is a very important characteristic of the superconductors because it is a particular field above which you have that vortices are free to move inside your sample. So you have that the pinning is equal to 0. So for the application, it's very important to take and to put your magnetic field below this irreversibility field. Otherwise, you have that your vortices moves around in the sample and are dissipating also energy, and this is to be avoided for applications in general. So also these characteristics can be very important. In particular, we have extracted from these curves, and we have obtained this picture that characterizes the reversibility field as a function of temperature for the two samples. Now we can see that the reversibility field for the silver doped sample, that is this red one, is almost two times higher at T equal to 0 Kelvin, but also at lower temperature, at this low temperature, it is higher respect to the undoped sample. When we are moving near the critical temperature of the samples, the values are almost equal, we can say. Also for applications that in which we are involved to consider low temperature 2.5 for Kelvin usually is also temperature for applications, you have that this silver doped sample is better in the reversibility field values respect to this undoped sample. Now, we can extract also another characteristic from magnetization measurements. In particular, if you consider your magnetization as a function of time, you can study the so-called magnetic relaxation phenomena of the sample. This is very important because by means of this measurement, you can extract the pinning energy values of your sample. And in particular, in this curve that shows the magnetic relaxation phenomenon, you can see how the undoped relaxation phenomenon curve is much noisier than the silver doped one. And this indicates another time that a stronger magnetic background is present for the undoped sample with respect to the doped one. Now, from these curves, the important characteristic that you can extract, as I said below, as I said previously, it is the pinning energy as a function of the magnetic field at temperature equal to 2.5 Kelvin in this case. Now, you can see that for low magnetic fields below 1 Tesla, around 1 Tesla, the pinning energy behaviors are similar for the two samples. But when the magnetic field increases, you have that the pinning energy values of your samples for the silver doped one decreases slowly with respect to undoped sample ones. And moreover, these curves can be fitted by this power law, where this exponent alpha is very important because it indicates the vortex spinning regime that is acting in your sample. And in particular, when alpha is near to 0, we can say, yeah, that your pinning energy is low dependent from the magnetic field. This means that you are considering a single vortex spinning regime, and it means that the vortices are pinned very strongly and independently among them. So, while when this alpha, this is not so clear, I don't know why, but it is 0.65 and 2.2. So when you have that your alpha values are above 0.5, and this is the case, you are considering a collective pinning regime that is a weaker state of pinning regime, in particular that the vortices are interacting with each other. Now, you can observe also and extract also this crossover field between single vortex state and the collective pinning regime. And for the undoped sample is 0.79 Tesla instead of 1.34 Tesla for the silver doped sample. The important characteristic is that for high magnetic fields, and you want to use these samples, for example, for applications in high magnetic fields, you have that the silver doped sample has a slow decrease of the pinning energy as a function of the magnetic field. So, the conclusions are shown below, and in particular, by means of DC magnetic measurements, we have determined that the addition of this 6% in weight of silver in our iron selenium material increases of approximately 0.5 Kelvin the critical temperature. The second property that we have observed is also that the doping with silver shows a clear improvement in transport properties, that is the critical current density of the sample, and measured as a function of the field. Moreover, we have also shown higher irreversibility field values at low temperature and also at T equal to 0 Kelvin, that in which the irreversibility field was almost the double with respect to the undoped sample. In particular, also, both samples undergo to a pinning crossover, as we have seen, from a single vortex regime to a collective pinning regime. So finally, we can conclude that the presence of silver in the lattice acts as pinning centers, improving the overall flux pinning features of the sample. And with this last picture showing the Meissner effect reproduced at the European Manifestation Futuro Remoto 2017, I thank you all for the attention.
Are there any questions?
Okay, I have first it's quite too far for my side.
Maybe it's not related to
to your presentation, but you classified the iron superconductors at the beginning of the presentation. I've seen that the group you considered is iron and selenium, and I think I've seen tellurium, so all the chart events. Do they have a role in this classification, or it's just because it's group 6?
No, okay, good question. No, when I showed the several families of the iron base, there was 1, 1, 1, 1, 1, 2, 2, 1, 1, and 1, 1, 1. These numbers are related to the stoichiometry of the samples. So if you have iron and selenium, you have that.
The properties change.
Yes, because for lack of time, I have not shown you the crystalline structure of these samples, but this is composed by layers, and in particular, the iron selenium layers give the superconductivity to these samples. And so you understand that if you have a layer composed by only iron selenium, or iron selenium, tellurium, and other elements, for example, the properties can change very much. In particular, the strongest family in superconducting property is the first one, 1, 1, 1, 1, that has 4 elements usually for giving you the compound. So the answer is yes, that these belonging to these different families can change the properties. In particular, the family 1, 1 is the simplest to fabricate, but you have the counterbalance that you have not so, you have strong properties, but lower than the other families. But it is easy to fabricate, and it is not also poisoning. So it is also useful for the researchers that are fabricating this sample.
Okay, thank you.
You're welcome.
It's just a curiosity. You told that you're using an experimental stuff. It's not requiring the cooling with the liquid helium. Or I have missed it, or you did not explain how is it.
No, exactly. No, it is, the system is dotted this option level called 2 of a cold dead that, in particular, you have a compressor that expand your gas and use a compressor to lower the temperature of the helium gas. The important thing is that you put by means of a bottle, and it's also okay. This one. So you use only helium gas bottle for putting inside the viewer the helium gas, and by means of this cold dead, you are able to lower the temperature of this gas and to liquefy the helium gas. So you have only a mechanical compression of the, in particular, of the helium gas. Before of using this system and this cold dead that can liquefy your helium, you have to put directly the liquid helium inside the viewer. This was very expensive because initially it all evaporates, and after that it begins to liquefy in your viewer. But you have to spend for cooling down your system 100 liters of helium, for example, and 1 liter costs 12-13 euros. So you understand that only for cooling down your system, you have to spend 1,300 euros. Instead, with this system and with using alpha bottle that costs 100 euro, you are able to cool down your system and to use for several times, for months. So you understand that is the cost of the this is the problem. That only the option is I think 100,000 euro. Only the option. If you want to buy the entire system, it costs 300,000-400,000 euro. So you have to find this money, obviously from a project, European project, I don't know, because if you want to buy it, it's not 1,000 liter, it is 300,000-400,000. But if you measure with only liquid helium, without this system, this option, all the year, you spend much more in the costs of liquid helium for buying the viewer and viewer and viewer. You can measure 2 months per year without this option, or almost in around that months. But it is convenient for the costs of helium, but it is not so much convenient because it costs 100 diesel. So it depends on, I don't know, how much money you can spend. But we are from 5 years and we are measuring every day, so with a cost that is very, very low. So if you are able to find some money from, I don't know, European project, something, I can suggest you to to buy this option because it is very powerful. It's incredible. So this is the situation.
Okay, I have just a curiosity. If the 6% doping is a best case scenario, or there are other kind of doping, other level of doping giving me
yes,
other kind
there are several levels of doping that you can use. And in particular, there are some publications on this. We have published these results on 6%, but there are also studies that consider 2%, 4%, 6, 8, and 10. Particularly, there are these levels, but the best one is the 4% in weight of silver doping. So this improves your properties, but if you use 4%, it is not so much, but slightly better in binning energy, in critical current density. But 4 and 6 are very, very near as results and as properties. But if you put, for example, 2% or 10%, especially, you have a lowering of the superconducting properties because you are putting too much silver in your sample. So in that case, the silver does not act as spinning centers, but act as an obstacles for the flowing of the current inside the sample. So there is a perfect level of silver. It is around 4-6%. If you exaggerate in putting silver, or you are putting 2%, for example, you are not improving your superconducting properties.
Okay, thank you. I asked just because it's a quite young technology, and so
yes.
I want to know if there are other tries to find the best.
In recent years are performed several types of doping, but also with other elements. Silver is one element, but there are also other elements. So with the tellurium, for example, and other elements, because this is a very new branch of research, but with many perspectives. So it is useful to study the doping, how it interacts with the original sample, you can say.
Okay. Thank you very much. Now the matter physics session is concluded. I leave you for the.
Thank you. Just a couple of announcements. So we have just like 15 minutes of delay in the timeline. We try to reconvey here as it is in the program, so 10 past 2 p.m. so that we are in line with the rest of the program in the afternoon. During the lunch break, please try to stay next to your poster so that we can use also the lunch break to discuss a little bit the poster session. And I also invite the speakers of the next session that will be chaired by Giorgio Viavattene to bring here their presentation on a pen drive so that we can upload that to the PC that we are using for the presentation. So, thank you and have a nice lunch break.
Solo curiosità. No, no, ma stava provando da qualcuno, ma io dico per da vicino,
Ok, ciao.
al gruppo, sì, qualcosa. Sì, questo che hanno accettato così.
E questi proprio brutti da morire.
Era una giornata bella ieri.
A parte Villa Mondragone, a parte Villa, adesso a parte la Villa dove siamo stati.
No, 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 dico per loro, per loro.
Ah, beh, sì. Ci vediamo dopo.